will cross. So it will go up. So before cross-slip, it will join. Okay, and then this part will cross-slip, and every segment will cross-slip, and this is how it will go up. So the role of this cross-slip is defined by stacking fault energy. If the stacking fault energy is high, then cross-slip will be easier. If it is low, it's not. Okay, so barriers can be crossed even at lower temperature or room temperature. When you don't have enough vacancies to cause climb, even then barriers can be crossed by cross-slip. Okay, and then you are not changing maybe the stress values. Okay, so let us come to that question, that why materials will break in fatigue but not in monotonic loading at lower stress. So when you are doing monotonic loading, then you have to create plastic deformation in every grain. Okay, and then plastic deformation has to go to the level of damage, because all the dislocations are moving in one direction. Okay, but when you have cyclic loading, so your stress values are going up and down and up and down. In that case, dislocations are moving in one direction, then coming back. Not all of them are coming back. Okay, so there is some amount of irreversibility. So in every cycle, however insignificant it is, some amount of strain is irreversible, and this gets accumulated. Okay, dislocation movement is a plastic deformation. There is some amount of plastic deformation which is remaining. It is not fully recovered by changing the direction of the stress. Okay, and this will get accumulated. This accumulation will be very small initially, but then for very high number of cycles, if you do it, then this strain accumulation will increase, because it is getting accumulated in each number of cycles. As you increase the number of cycles, it will increase, and then there will be a point where no more plastic strain can be accommodated by the material, and then there will be damage, then there will be failure. Okay, so the stresses are lower, but the role is played by the number of cycles. So obviously half of this cycle is monotony, so this part is still monotony. So if you apply a stress which is lower than yield strength, in this cycle it is not going to break. Okay, so stresses are lower than yield strength, but if you apply it too many number of times, then it is going to break the material. Okay, so usually the test is done, the conventional fatigue test is done on a sample which looks similar to a tensile sample, and we will discuss the reason why later on, but the surface of this sample has to be very, very smooth, not like tensile sample. So you have to create higher surface smoothness. So mirror polishing you have to do for this fatigue test to be done. Okay, and then it will be connected to shafts which will be rotating, and this will cause fatigue loading on this, and it will break the sample. Okay, so you will have a weight connected here, and so when it goes up there is a tensile loading, when it goes down there is a compression. So it's actually doing this only while it is rotating. It has to rotate because the same dead lift can cause tension and compression both. Not tension and compression, but reverse direction of loading. In each cycle you will have tension. So when it is in the lower side, then you have tension on the upper fiber, compression on the lower fiber. So it is bending basically. So it is called rotating bending test, and it was discovered by Murray. So it is also called J.J. Murray's test. So you do this kind of testing at different values of stresses, and then you load it for different number of cycles. So you don't load it for number of cycles, you basically load it for different values of stresses, and then you see when it breaks, and you count after how many number of cycles it has broken. Okay, So then you can plot various things. So you can plot, for example, delta sigma, which you have applied. So let us look at those variables. So this is the maximum amount of stress which you are applying, and this is your minimum amount of stress which you are applying. Okay? So what is the amplitude?
Maximum minus minimum.
Maximum minus minimum. So that is your delta sigma and that is your amplitude of the stress. So stress amplitude. Then you will have a mean value. What is the mean value? Sigma max plus sigma min divided by 2, average value. Okay? So this will be mean in this case if this is equal to that in magnitude. Okay? So if this is plus 500 and this is minus 500 megapascal, then your mean stress value is 0. Okay? So you can plot various variables. You can plot delta sigma or you can plot sigma mean, and for sigma mean you will have to write here what was the amplitude, because 0 sigma mean will not give you any value. Then there is another parameter which is called R, which is just the ratio of sigma max and sigma min. Okay?
So sigma minimum upon maximum.
Yes. So, okay. So if you plot stress variables, you can also do strain loading. Okay, instead of applying stress amplitude, you can also apply strain amplitude. So let us look at this, and then if you do this kind of testing at different number of cycles, then as you increase the number of cycles, you need lesser stresses to break it. Okay? Or you can also go backwards. So if you increase the stress, you need less number of cycles. Okay? Stress amplitude or mean, both will cause this. Okay? And then, so this goes to 10 to the power 6 number of cycles. Okay? Well, the real data will not be this smooth. You will not see this kind of line. The real data will be having a lot of scatter, not a little bit of scatter. This scatter is as good as the scatter we have seen in ductile to brittle transition. Okay, so if I plot this, then you can see that for this stress value you can have samples like this. So some samples will break at this number of cycles, some will break here, some will break there, some will break there. Why do we get this huge scatter in this? There is a reason for getting scatter in ductile to brittle transition, because you have different number of secondary phase particles which are sitting at the crack front, and that decides, that is statistics, apart from a few other things, decides the differences in the value. In this case, what is causing this scatter? So you can think about it. So the usual curve looks like this, and then you see that there is a stress value below which if you apply the stress, it will never break. So that is the extrapolation of data. Okay, we do some testing in some range, and then we see the trend, and then we think that it should be like that. So up to 10 to the power 6 number of cycle, people did a lot of testing, and they found that for many materials it shows this kind of behavior. For some material it doesn't. Okay, for some material it will be just going down only. Okay, but design people need some simple things. They don't want to deal with a lot of statistical scatter. They are not interested or bothered about what is going on in material. They just want to know a value so that they can decide that ठीक है, इसके नीचे है तो pass through the material. And that value is this value. So if you keep it below this, then it is not going to break. and that is called endurance limit. Okay, so these are those salesmen or women जिनको कितना भी target दो they will achieve it. That target obviously has to be lower than the amplitude which you are saying. Okay, so this is something which is also good to realize when you are dealing with a team of people, that which person can take how many number of cycles or how much amount of stress amplitude the person can take. If the person is performing well, you can try increasing the stress by increasing the target, but then you have to observe keenly that if there is any damage coming in the person, okay, so then you have to stop. There is no infinite amount of number of, so even if the stresses are lower there, so what it says that for lifelong you can load him or her and they will keep on performing in the same way. That is not the truth with people, that is also not the truth with the material. So this was for a very long time, it was the idea in the section of design as well as with the materials engineer, that there exists an endurance limit below which material can take infinite number of cycles if the stresses are lower than that. But that idea was floated by the data which was obtained only to 10 to the power 6 number of cycles, and the prediction was made for more than 10 to the power. When you say infinite, that is obviously more than 10 to the power 6. Okay, so then some people were curious. A lot of people who are not that curious and they get timely salary and not bothered about solving questions, they will obviously not do the testing. Okay, they will take a theory and then well, this is fine, this is done. And a lot of times when you come with a stupid question to somebody, they will say it is already been done, there's no point in doing it. That shouldn't kill your curiosity. So some people were curious and they did the testing beyond 10 to the power 6 systematically, and they found, and this was done in 1984, not very recently. Even after that, for 20-30 years, even now, you will see the concept of endurance limit in books, well established, although it is not the truth. So 84, 89, NITO does a test with a scheme and finds that it is failing. It is failing when you go more than 10 to the power 6 number of cycles. The other idea was that there was no component which will go beyond 10 to the power 6 number of cycles in those days when it was done. So nothing will go beyond 10 to the power 6, but then people started developing different components which are going more than 10 to the power 6 number of cycles and they are breaking. So then those tests and then new tests were done to conclude whether there is really an endurance limit or not. Okay, so what is happening is that strain in every cycle is getting accumulated, and this strain accumulation gets continued for a very large number of cycles to whatever number of cycles you are loading it. If the stresses are very small, then this strain accumulation is going to be very small per unit cycle, so it will obviously take very high number of cycles to break it. Okay, it's not that there is no irreversible strain in the material. If that happens, only then it can take infinite value number of cycles. Okay, so this curve is called SN curve because you have stress and you have number of cycles on the x-axis for failure. Okay, and the part where stresses cross the yield strength, so that means you have plastic strain also in the material, that is called low cycle fatigue. So those things will break in comparatively low number of cycles, small number of cycles. And when the stresses are lower than yield strength, then you will have to have more number of cycles to break the material. So this regime is called high cycle fatigue, this regime is called low cycle fatigue. And there are equations for high cycle fatigue and low cycle fatigue. Different equations, and those two different equations can be joined so that the whole curve works. And that we will discuss. Coffin-Manson law and Baskin's law, and that we will discuss in the other class. And then there is the region where this goes down, and it will go on for a long time, then it will go down and on and so on, and then for other materials it simply goes down. And for both of them there is no endurance limit, it decreases. So that regime is called very high cycle fatigue regime. So this is LCF, this is HCF, and this is VHCF, also called GHCF, giga high cycle fatigue. So going to 10 to the power 10 cycles. Very is not controlling the number. Okay.
सर इसमें ग्रेजुअल लोडिंग तो नहीं करते होंगे ना?
किसमें?
जब फटीग टेस्टिंग करते हैं सडन टेंशन एंड कंप्रेशन करते होंगे.
Are you talking about the rate of loading?
Yes.
Rate of loading varies. You can do sudden loading and you can do gradual loading.
So जैसे इसमें टेंशन एंड कंप्रेशन होती है साइक्लिकली, तो इसमें टेम्परेचर का इफेक्ट नहीं आता. जैसे आपने कहा था कि वो टेंशन
आता है. So we study creep, we study fatigue, monotonic loading in chapters, right? But none of these things are happening in isolated way in the material. Okay. So monotonic loading is happening to an extent in fatigue where you are stopping it and then you are unloading it. Okay. So you are not going to yield strength maybe, or you are going to this part of the stress and then you are unloading it, reloading it, and so on. That's what you're doing. And also in monotonic loading, if this is the curve which you are seeing at one strain rate, so the rate of loading, how fast have you loaded? And if you change the rate, so if you change the speed of loading, then the curve will go like this. And if you keep on doing this, then it will go like this, then it will go like this, and then it will go like this. So strain rate effect is in certain range of speed, it is equivalent to the effect of temperature. So increasing strain rate is equivalent to decreasing temperature. Okay, but beyond a certain speed, it becomes adiabatic. It becomes high velocity, high impact kind of thing, and there you have mechanical wave phenomena which starts happening in the material. Okay, and in some materials, even this kind of fatigue can generate heat from inside. For example, rubber. If you heat it, the mechanical energy is not completely dissipated in the material. So it starts generating heat from within. Metallic materials will not do that. It will get heated up for sure. Some heating will be there because not every speed is isothermal. Okay, so some heat will be coming in the system, but in polymers this speed, so this heat is too high, so high that it can melt the material. Okay, so what you are saying will be seen in the effect of this. So when you are applying the stress with whatever strain rate or loading rate you are applying, the response you will see in the strain curve. Okay, the response of this you will see in the strain curve, and that you will have to plot on this kind of curve, stress strain curve, and you have to make now 4 quadrants for that. So you go and load it to sigma max, and then you unload it. Because it is higher than yield strength, you will have some amount of strain which will recover with unloading, and then you are loading it again in the reverse direction, and yielding will start, and then you will unload it. It should come back to the same point. It will not. because of Balstringer effect, because of adiabatic heating, it will not come to the same point, and then you will have a hysteresis loop. That is the amount of heat which is generated per unit cycle in the system. Okay, and then if you lower it over and over again, what will happen? So you can do it in two ways. One is that you say that my stresses are constant, so my sigma max is this and my sigma minimum is that. Okay, so when you go for the next cycle, what will happen that it will achieve sigma max at smaller strain. Okay, and then you will unload it, and then also on the lower side it will achieve at smaller strain, and it will go on like this. So what is happening? For the same amount of stress, the strain achieved is less. So the material is getting stronger. You can also have an effect where more strain will be there for the same amount of stress. So strain hardening can happen, strain softening can happen. Similarly, you can have a situation where you apply constant strain. So you say that this is my highest strain and this is my lowest strain. So you load it so that it comes to this value of strain. Or you can define this as total strain also. So you can say that this is your epsilon max. Okay, and then it comes back and it goes there. Oh, so here will be my epsilon minimum, and in the next cycle what will happen, that to get to the same value of strain you will have to apply more stress. Okay, so this has to go higher like this, and then it will come back, and here also it will go higher, and in every cycle you will see that it goes higher and higher. Also on this side. So it means that material is getting stronger per unit cycle, and this will saturate after some time. After some time there will be no more strengthening. Otherwise, if the strengthening continues, then it will be a very good manufacturing process to make something very stronger, because we just have to load it for a number of cycles, and then we don't have to work with super alloys or something. Okay, so this has to stop at some point. Every material has some capacity. So again, the same analogy, people will show some resistance to the stress, and that resistance itself will cause the damage in them. So that will stop at some point. Okay, so we'll stop here and we'll continue in the next class.